All right, welcome back everyone. Continuing on in this topic of spatial regression. Last time we had a review and we introduced ordinary least squares. This topic is on ordinary least squares, going through an example and highlighting some of the things that we talked about with the 6 checks. Modeling spatial relationships has a lot of different options that you see here. Today's class, we're going to work primarily with ordinary least squares. And last time, remember that correlation does not mean causation. We have 6 checks to properly specify our model. Now again, these are 6 checks that are, to be honest, sometimes difficult to meet. So a lot of data gets used, a lot of data gets published that doesn't pass all these 6 tests. But we should strive to this. If you don't pass these 6 tests, you have some major limitations in what you can do with your model output. All right, so that said, here's what we're looking for. Coefficient should support the hypothesis, plus or minus on their sign. Explanatory variable should be significant. Residual should not be clustered in location. We can use Moran's I to test for that. And a residual should not be clustered in value. That's the Hark-Barra test. And each variable should explain part of the story, the variance inflation factor, and the overall model performance with adjusted R-squared. So on to the data. The data for this exercise is the Appalachian Regional Commission, that's the ARC, county water data. So we're specifically looking at water data and a lot of the variables that were put together for this ARC region. The dependent variable we're going to use to model for this region is the flood total, the number of floods that have occurred over a 10-year period. And there's a bunch of independent variables which are going to be used to try to explain why that flood total is what it is for that particular county. Dependent variable again is flood total for total floods. Just a little bit of background on this. This flood data was provided by the National Climate Data Center at the National Oceanographic and Atmospheric Administration, which is NOAA. The data was compiled from storm data from 124 regional offices of the National Weather Service. And we queried this database for events between September 2000 and August 2010, looking for flood and flash flood categories. This is showing those flood totals for the region. So you see the pinkish color having the most number of floods that have been recorded as part of this database. So trying to explain why those counties have high floods is what we're going to try to do with our model. It's important to look at the other variables that exist in that table, which are going to be our independent variables or the explanatory variables. So one is the stream name. You can't have a flood or flood event and so on without water. So this is the stream length for each of these counties. Now it's NRM, which means it's normalized. So we have the highest number of streams per county, and that's divided into all the other counties to get a normalized value and multiplied by 100. So we get values between 0 and 100. That's what the normalization was done for. Important just for the scaling factors of all this area. Another independent variable is the normalized lake totals. So this isn't 100 lakes in the top. It's the highest number of lakes per county could be, say, 5. And that value of 5 is then divided in the rest of them and multiplied by 100 to get your 0 to 100 range. Again, normalized like the other one. Lakes are important because we don't have in this region, we're just south of the Finger Lakes up here, so we don't have a lot of glaciated lakes that were created. So there's not that many natural lakes of considerable size either. A lot of the lakes are impoundments or created for flood control. Here's the groundwater normalized values. So these groundwater values are important to consider based upon the ability of the ground to handle additional inputs, and that groundwater score is normalized again for each of those counties. So the areas that are in darker, kind of brownish red here, are areas that have a higher groundwater potential score. Now, the ordinary least squares command is activated from the ARC toolbox, or you can just do a search for OLS. This will come up. So our input are the ARC counties that have water-related variables that have been summarized. We need a unique ID field just so you count each of the records uniquely. That's all it does. So you need to have a field which has a corresponding record number for each of the records, for each of the point locations or polygons in your data set. So that's all it is. It's just a unique identification field. And the output feature class, this is going to be run1. So this is going to create a brand new shapefile based upon this ordinary least squares. Dependent variable, I have flood total. And then from this list, you can't see all these variables, but you're going to go through and you're going to find stream normalization, lake normalized, and groundwater normalized. You just put a little checkbox in them just like this. So, scroll down, find them, and check them. The output report file is a PDF, and then there's a coefficient output table, and there's a diagnostic output table you should also specify. So I like to specify these. I have both of these being created in the same folder. I have a C-temp topic 8 folder in which I'm putting this output. All right, so again, ordinary least squares, we're performing a global model run, trying to fit this linearly to predict the number of floods, the flood total, using these explanatory variables as a first run with this, calling this run 1. All right? And this is what the output looks like. So we have the standardized residuals, which are mapped as part of our output. And looking at the red areas, those are standard deviations above for those the standardized residuals. So you see some areas that are way above the fitted line, those are the red, and areas that are way below are more the bluish color. Doesn't seem like we have any that are 2.5 in the negative standard deviation size below our observed values compared to the predicted as part of this. Looks like there's much more on the higher side of our predicted line. All right, so that's our model, and we have a prediction for those floods, and we can also, if I go back when running this command, so these are all filled in. The output, after it says it's run, gives you a nice message here saying that you need to basically make sure that you don't have spatial autocorrelation occurring, the Moran's eye tool, to assure that those residuals are not spatially autocorrelated. And as part of the view details, this is the report, so we can see a summary of those OLS results. We can see the different coefficients, t-statistics, probability scores, and so on. So all this is just kind of a quick view details of your model run. But don't forget, we specified an output report file, coefficient table, and the other table. This is the PDF file. So this file right here, run1 report, was created, and that's what I'm viewing now. It has 6 pages. So we can look at this based upon those 6 checks, and we can go through each one of these factors to see if it passed this particular test. So here's a summary of the OLS results, the model variables, the diagnostics. As you can see here, kind of everything summarized. Okay. We have variable distribution and relationships between each of the variables. These are histograms and scatter plots, how each variable is distributed. We also look for normality of our residuals. So this is the normal fit of what we're looking at for those histogram of the standardized residuals. And this also shows us the residuals versus the predicted plot. And then the last 6th page is the ordinary least squares parameter. It's just showing other variables and what was dependent and what were the explanatory variables and what was the specifications of the model run. Other things that were created as part of the output were the run1 coefficients and also the run1 diagnostics. So this gives us all of our diagnostic results as well for that particular model run. As you can see, not a very good adjusted R-squared for this particular model in terms of the predictive power. So one of the things that we talked about that we need to do, is one of the checks, is to make sure that our residuals are not spatially autocorrelated. So we're going to run the global statistic of spatial autocorrelation global Moran's I using the run output from the OLS. Our field is the standardized residuals, and we're going to generate a report. Inverse distance is our spatial relationship, and we're not going to do standardization for this Euclidean distance. So this is going to create an output report file to test for spatial autocorrelation. So when it runs, we say view details down here, and then the report file comes up. And I highlighted this area right here because this is the HTML file. So when we highlight this HTML file, what we notice is that it fires up in our browser, and we can see that those residuals from the spatial autocorrelation Moran's I test are very clustered. So that doesn't pass that particular test. Our residuals are clustered, and that's not a good thing. So I didn't really spend a whole lot of time going through those other tests. I wanted to focus on the global Moran's I stats test for you. But this is essentially a test which tells us that we're going to have incorrect results, biased results with this particular model because our residuals have such spatial autocorrelation in them. So we're going to be able to, we need to get in and fix this now, and some of our options to do this are with geographically weighted regression, which we'll talk about pretty soon. Alright, so that's running the OLS model. That's having some output results, and that's also running the global Moran's I, or spatial autocorrelation tests. And again, we conclude from this that because of our residuals are clustered, we have spatial autocorrelation existing in our model, essentially biasing our results.